So in this example, you're using a slingshot to fire a rock, which has a mass of 45 grams, at an angle to the ground. Notice that in this unit, in the energy unit, we don't even care what that angle is, because when we're dealing with energy and conservation of energy, those are scalar quantities, so we don't actually care about the angle the rock is launched. The rock is 1.23 meters above the ground when you stretch the elastic 5.6 centimeters before you release it. If the spring constant of the elastic is 62 newtons per meter, determine the speed of the rock when it hits the ground. So in this case, I've got some sort of a slingshot, and I've got some elastic that I'm stretching, and I've got some rock right here. In this particular question, the reference height that I'm going to use is just going to be the ground, since that's the easiest reference height. I'm told that just before I release the rock, it's got some height, 1.23 meters above the ground. And I'm told that when I stretch the elastic, it's got some stretch of delta x. That delta x was 5.6 centimeters. But don't forget, whenever I'm using the equation for elastic energy, delta x is always in meters. So I want to make sure that I remember to convert that to meters. Since I'm on conversions, I've got a mass in grams. I need to make sure that I always convert that to kilograms as well. That's a kilogram. Okay, so down here, I'm going to use the idea of conservation of energy. So I'm going to need to choose a couple different points in the motion of this rock. This is obviously going to be point 1, where I have a bunch of information. When I release it, sorry, I'm going to write right over that. The rock is going to follow some trajectory, and just before it hits the ground, I'm interested in knowing the speed of the rock at that point in time, so I'm going to call that point 2. Conservation of energy tells me the total energy at point 1 is equal to the total energy at point 2. So there are a bunch of different types of mechanical energy in this question. I've got some gravitational potential energy at point 1, possibly some kinetic energy, possibly some elastic energy. Same thing at point 2. Maybe I could have some gravitational, kinetic, or elastic energy. So I like to start my conservation of energy problems by stating this right off the bat. Then I can go in and say, initially, yes, I have some gravitational potential energy at point 1. I don't have kinetic energy because the rock is stationary initially. And yes, I do have some elastic potential energy at point 1. Finally, I don't have any gravitational potential energy at point 2 since the rock is at my reference height. I do have some kinetic energy since it's going to be moving before it hits the ground. And I no longer have any elastic potential energy just before it hits the ground. So this simplifies my equation. I know that the equation for gravitational potential energy is mgh. I know the equation for elastic potential energy is 1/2 k delta x squared. And I know kinetic energy is 1/2 mv squared. I'm using subscripts to keep track of heights, extensions, and speeds at different points in the motion. And that's going to help me when I have more complicated problems. In this case, I can't cancel anything out because every single term has different variables in it. But I would like to rearrange for v2, this variable here. So I'm going to multiply both sides by 2. So everything on the left-hand side, everything on the right-hand side. So now I've got 2 mgh1 plus k delta x1 squared equals mv2 squared. Rearranging this equation, I've got 2 mgh1 plus k delta x1 squared all over m. Don't forget, I will need to take the square root of both sides, so I can do that right now before I sub in numbers. You don't have to, but I will. So now I'm at the point where I can substitute in some numbers in. The mass was 45 grams, 0.0450 kilograms. G is 9.81. Initial height was 1.23 meters. My spring constant K is 62 newtons per meter. The extension is 5.6 centimeters, which is 0.056 meters. I'm going to make sure I extend my square root sign the whole way across so that everybody knows it's all under the square root sign. Finally, I'll divide by the mass again, and that's equal to V2. So let's take it one step at a time so we can keep track of significant figures. This first term here, when I calculate this, which I've done before now to make this a little bit shorter for you, 1.085967. I'm going to round to 3 significant figures, so I'll just put a little arrow to keep track. The next term is equal to 0.194432. Here, I'm rounding to 2 significant figures. I'm going to divide everything by the mass again. And that's equal to V2. When I add up those two terms, I'm going to be rounding to the hundredths place, since that's my least precise decimal place. So when I add up the numerator, I'm really leaving a lot of room under the square root sign. You don't have to. I get this number, which I will round to the hundredths place, divided by my mass. So my final answer is going to have 3 significant figures. 3 significant figures on the numerator, 3 significant figures on the denominator. And when I take the square root of a number like that, I end up with the same number of significant figures. So the final speed is 5.33416 meters per second, rounded to 3 significant figures. Therefore, the speed of the rock is 5.33 meters per second before hitting the ground. We solved lots of problems like this in the forces unit, except we had to figure out velocity and not speed. So it's kind of nice for a change of pace to just deal with the magnitude of the velocity for once and ignore direction.